Tesla built a 187-foot tower on Long Island with one impossible goal: power the entire world wirelessly. No cables, no plugs, just pure energy traveling through the Earth itself. His Wardenclyffe Tower wasn't just another invention. It was humanity's first attempt at planetary-scale wireless power. But here's what Tesla didn't know. Physics had other plans. The same exponential decay that kills your phone's wireless charging over a few inches would demolish his dream on a global scale. Yet modern engineers are finally cracking the code Tesla couldn't, and the breakthrough isn't what you'd expect. But before we get there, let's step back and look at Tesla's original blueprint. Tesla's blueprint was nothing short of planetary engineering. He didn't just want to power your house wirelessly, he wanted to turn the entire planet into a giant electrical circuit, with Earth itself as the conductor. This wasn't about convenience. It was about fundamentally rewiring how humanity accessed energy. Tesla's master plan for Wardenclyffe stretched far beyond that single tower on Long Island. He envisioned a network of transmission stations spanning continents, from Newfoundland to Scotland, from Colorado Springs to the European coastline. Each station would pulse electrical energy into the ground, creating a planetary grid that made traditional power lines obsolete. The audacious assumption at the heart of his design was simple but revolutionary. Tesla assumed electrical energy could pulse through the ground like blood through veins, reaching every corner of the globe with minimal loss. He imagined Earth's crust and atmosphere as perfect conductors, ready to carry massive electrical loads across thousands of miles. Ships would light up in the middle of the Atlantic Ocean, drawing power directly from the planetary grid beneath the waves. Cities would eliminate every power line, every transformer, every cable. Aircraft would pull energy straight from the atmosphere, never needing to land for fuel. Tesla's vision extended beyond pure power transmission. He planned to encode information within these electrical pulses, creating the world's first wireless internet decades before anyone understood what that meant. Messages, telegraphs, and data would ride alongside the energy waves, connecting every corner of the planet in a single integrated communication system. He calculated it would be more efficient than copper wires, believing the Earth and atmosphere would act as low-resistance conductors, an assumption later shown to be incorrect. The engineering behind Wardenclyffe reflected this planetary ambition. The 187-foot tower sat atop a 120-foot deep well, specifically designed to tap into the Earth's electrical characteristics. Tesla believed this deep grounding system would allow him to inject massive electrical currents directly into the planet's conductive layers. The tower's copper dome would simultaneously broadcast energy into the atmosphere, creating dual pathways for global power distribution. Every measurement, every specification was calculated to maximize the Earth's natural ability to carry electrical current. Tesla's confidence in this approach was absolute. He believed he had solved humanity's energy problem forever. No more coal plants, power distribution networks, or energy scarcity. The entire planet would become humanity's first wireless charging pad, delivering unlimited power to any device, anywhere, at any time. Tesla saw this not as an invention, but as the inevitable next step in human technological evolution. But Tesla's grand vision rested on assumptions about physics that would prove catastrophically wrong, the physics trap that killed a dream. Tesla's wireless power demonstrations could light up a room and create spectacular electrical arcs, but the same physics that made them possible also guaranteed his global network would fail. Those mesmerizing displays weren't just showmanship. They revealed the fundamental mechanism behind wireless power transmission. Tesla coils operate as high-voltage, high-frequency generators that create rapidly changing magnetic fields. These oscillating fields induce electrical current in nearby objects without any physical connection, lighting bulbs across the room and sending sparks dancing through the air. The magic happens through electromagnetic induction, the same principle that powers transformers and generators worldwide. When alternating current flows through the primary coil, it generates a magnetic field that expands and contracts hundreds of thousands of times per second. This changing field cuts through space, inducing voltage in any conductive material within range. Tesla's demonstrations prove this concept worked brilliantly over short distances, creating enough induced current to power light bulbs several feet away from the coil. But Tesla didn't fully grasp the fundamental limitation that would destroy his global ambitions. Field strength falls off very rapidly with distance. What lights a bulb feet away becomes negligible at longer ranges. Double the distance from a Tesla coil, and you lose roughly 6 times the power. Triple the distance, lose 14 times the power. This rapid drop-off makes long-range wireless transmission impossibly inefficient using electromagnetic induction alone. The math tells the brutal story. Tesla's demonstrations work because they operated over distances measured in feet, not miles. A bulb that glows brightly at 5 feet will barely flicker at 50. Scale that up to continental distances, and the power loss becomes astronomical. Tesla's tower would need to generate millions of times more energy than necessary just to deliver a usable amount thousands of miles away. Tesla's critical misconception ran deeper than distance limitations. Tesla assumed the Earth and air were excellent conductors. In reality, both are poor conductors, so ground-based transmission would suffer huge losses. The energy losses through ground transmission would be enormous, making his planetary grid physically impossible with available power generation technology. Tesla was working at the absolute edge of contemporary physics knowledge, building theories from brilliant intuition rather than the experimental tools that would emerge decades later. He operated in an era when electromagnetic field behavior remained poorly understood, before scientists had developed the mathematical frameworks to predict power transmission losses accurately. Modern physicists recognize that Tesla didn't know what he didn't know. His theories were based on incomplete understanding of how electromagnetic energy actually propagates through different materials. The same electromagnetic induction that made Tesla's coils spectacular also created the wall of physics that made global wireless power impossible with his approach. Yet Tesla's failed experiments laid the groundwork for wireless power solutions that actually work. From parlor tricks to pocket chargers. Your smartphone's wireless charger is a direct descendant of Tesla's coil experiments, using the exact same electromagnetic induction principle, just engineered for reality instead of dreams. Modern wireless charging borrows Tesla's induction idea, but adds resonant coupling, tuned frequencies, and precise coil geometry to make it practical. That sleek charging pad on your desk operates through identical physics to Tesla's spectacular laboratory demonstrations. A coil inside the charger generates a magnetic field that induces current in your phone's receiving coil, transferring power across the small air gap without any physical connection. The difference lies not in the underlying science, but in the engineering precision that makes it actually work. Modern engineers solve Tesla's distance problem not by overcoming physics, but by working within its constraints through precision alignment and optimized coil design. Contemporary inductive charging systems abandon Tesla's grand global ambitions in favor of millimeter-perfect positioning and carefully tuned frequencies. Resonant coupling works, but only across a few centimeters, so engineers control distance and alignment to get usable efficiency. The charging pad in your phone must align precisely because even small misalignments dramatically reduce power transfer efficiency. This isn't just about phone chargers. Engineers are pushing wireless power into applications Tesla never imagined. Electric vehicles can now charge by parking over special pads embedded in parking spaces, eliminating the need to plug in cables. Research projects explore charging moving vehicles using coils embedded directly in road surfaces, creating highways that power cars as they drive. Room-wide charging systems hide infrastructure within walls, automatically powering devices like phones and hearing aids the moment users enter a space. Each approach solves a specific problem: convenience, moving vehicle charging, or room-scale elimination of cables, rather than overturning the physics Tesla misread. Modern wireless power succeeds through smart, smaller steps rather than Tesla's single giant leap, achieving practical results through targeted applications. Contemporary systems prioritize safety, reliability, and energy efficiency, qualities Tesla's high-voltage demonstrations couldn't achieve at scale. Today's chargers operate at carefully controlled power levels with built-in safety mechanisms that shut down if metal objects interfere or temperatures rise too high. They use advanced materials and fine-tuned control systems that weren't available in Tesla's era. What looked like a parlor trick also proved a principle, but it lacks scalability. The key insight driving modern success is abandoning Tesla's global ambitions in favor of solving specific, high-value problems with engineering precision. Instead of trying to power the entire planet through one massive system, today's engineers deploy hundreds of specialized solutions that collectively eliminate cables from targeted applications. Medical devices can receive power through skin without surgical battery replacements. Industrial sensors operate in hazardous environments where cables would fail, but inductive charging still faces Tesla's fundamental limitation: distance kills efficiency. The next breakthrough requires abandoning electromagnetic induction entirely, breaking through the wall. Modern engineers are breaking through that wall using microwaves, lasers, and ultrasound, technologies that don't defeat the physics so much as create narrow, controlled energy channels where power arrives exactly where needed. Microwaves can beam energy across longer distances, but require precise focusing and careful weather management. Lasers deliver highly focused power with minimal loss but need clear line of sight and work best in vacuum environments like space. Ultrasound transmits energy through solid barriers and sealed devices, opening possibilities Tesla never imagined. These new approaches represent more than just an upgrade. They're a complete reimagining of how energy moves through space. Instead of repeating the mistakes that doomed Tesla's dream of global wireless power, engineers now work with the laws of physics. They use precision-targeted beams of energy, whether microwaves, lasers, or even sound waves, that can travel through air, vacuum, and sometimes even solid materials. Later, we'll break down how techniques like resonant tuning and beam shaping let power flow to specific devices instead of wasting energy trying to light up entire continents. But every method comes with its own challenges. Take microwave power transmission. Engineers are pushing its limits to deliver wireless energy across vast distances. Ground stations can beam microwaves up to satellites, cutting the need for bulky solar panels in space. The problem? Safety and precision. Atmospheric interference and stray beams are serious hazards, so the system requires extreme targeting. On the ground, microwaves also power sensors in dangerous places, where replacing batteries is impossible. Unlike short-range charging pads, these beams stretch across kilometers, demanding accuracy down to the smallest fraction of a degree. Now compare that to laser-based power transmission. Here, concentrated light beams carry energy with incredible efficiency, far higher than most traditional methods. But lasers need a crystal-clear line of sight. No obstacles, no clouds. That makes them perfect for space missions, where the vacuum of space eliminates interference. For satellites, rovers, and future deep space systems, lasers could supply clean, targeted power over vast distances. Then there's ultrasonic power transmission, which uses sound instead of radiation. Unlike microwaves or lasers, sound waves can pass through solid barriers that block electromagnetic energy. Imagine charging a device through a wall, or powering a medical implant sealed inside the human body. This method avoids many of the safety concerns tied to radiation, opening doors to applications Tesla couldn't have imagined. The secret to making these systems work lies in engineering precision. Resonant tuning matches frequencies between transmitter and receiver, squeezing out the maximum efficiency. Beam shaping narrows the flow of energy, guiding it exactly where it's needed, while keeping stray energy and safety risks to a minimum. And real-world uses are already taking shape. Spacecraft can draw energy from orbital power stations. Devices in hazardous environments can run indefinitely. No wires or batteries required. Everyday electronics move closer to true cable-free operation without the finicky alignment of today's wireless chargers. Each technology solves problems Tesla couldn't crack. His dream of universal wireless energy may have failed, but targeted solutions are proving far more powerful. In the end, it's not about lighting up the whole world at once. It's about delivering energy exactly where it's needed. Tesla's failed Wardenclyffe Tower wasn't really a failure. It was humanity's first serious attempt to engineer around the fundamental limits of physics, and every wireless device you use today carries DNA from those early experiments. The tower represents a pivotal moment when ambition met reality, creating the foundation for modern wireless technology. The future of wireless power won't come from building bigger towers, but from building smarter, smaller systems that work together to create the untethered world Tesla envisioned. Tesla's dream of wireless power is becoming reality through thousands of targeted solutions, rather than one grand gesture, proving that sometimes the best way to change the world is one device at a time. And maybe that's the real story. Tesla didn't fail, he just started something too big for his own time. The question now is who will finish it. If you want to explore how today's technology is finally catching up to Tesla's vision, subscribe and stay with us as we uncover the innovations shaping our future.